Section 2.7, Understanding Amazon Aurora's Fault Tolerance and Restoration Architecture. There might be some replication in here on things we've already gone over, but it's to refresh your memory to go on to some other things never covered before. You remember that each 10 gigabyte chunk of your database volume is replicated 6 ways across 3 availability zones and can be used as units of repair or hotspot rebalancing. Automated, incremental, and continuous backups are streamed into Amazon S3 for the 11 nines availability and durability in parallel and asynchronously. The log-structured storage nodes each have their own redo logs to generate pages on demand. At restore, backups are retrieved at the appropriate segmented snapshots and streams logs to storage nodes. There's a 4 to 6 write quorum with automatic fallback to 3 of 4 if an availability zone is unavailable. There's a 3 of 6 read quorum, and peer-to-peer gossip replication fills in the holes, ensuring that every node has the same data and that it's correct. An Amazon Aurora cluster contains the primary node and up to 15 replica nodes. Failing nodes are automatically detected and replaced. Failing database processes are automatically detected and recycled. Secondary nodes automatically are promoted on persistent outage, giving no single point of failure. With traditional databases, upon a crash, you have to find and make sure that the last checkpoint is good. Then replay logs from the good point before the crash, going back and forth to disk using many extra IOs, taking a lot of time. In addition, it's done on a single thread, which slows things down even more. Crashes require a reapplication of the SQL in the redo log since the last checkpoint. Let's contrast this with Amazon Aurora. Amazon Aurora's underlying unique storage replays redo records to each segment on demand as part of a disk read. They're parallel, distributed, and asynchronous. And there's no replay necessary for startup. The Aurora team moved the cache out of the database process. Therefore, cache remains warm in the event of a database restart, which lets you resume fully loaded operations much faster. Instant crash recovery plus survivable cache equals quick and easy recovery from database failures. This image shows a timeline of how failovers might happen and how they become more predictable from an Aurora standpoint. The top timeline is a MySQL database running on RDS. You have failure detection, whereby the RDS service is continually monitoring the master node to ensure it's healthy and the availability zone is healthy. When it detects there's a failure, it starts the failover process. That failover process involves moving to a standby database that you have hopefully running in another availability zone, and you fail over to that database. The recovery period is variable depending on how much data needs to be replayed from the log files and how much data has to be caught up since the master database went down and what the standby has. Then there's also DNS propagation that happens so that when the RDS service fails over from your master database to a standby, it changes the DNS entries to point to the standby, which is now going to be your master database. That can take anywhere from 30 to 60 seconds. At the end of that, your app is up and running, but there's a lot of unknowns, such as how long that might take. For Amazon Aurora, represented in the bottom timeline, you have your failure detection, and once that's determined, the recovery is almost instantaneous, because if it's a read replica, it already has all the production data, or if a new instance has to come into play, it's able to start reading data off the storage nodes immediately. recovery time is very small, so your application can be up and running right away. The Aurora team worked with the MariaDB team, who were able to create JDBC ODBC drivers that work with Aurora. With those drivers, they're aware of all the read replicas in your cluster. And what Aurora does is put an entry into all those read replicas of who the master database currently is. So when a failover happens, the RDS service informs all the replicas of who the new master is. And the MariaDB driver will resolve that and ensure they're always connecting to the master database. That means we can leave the DNS propagation out of the equation. And remember, Amazon Aurora supports cross-region replication. Now let's go over Amazon Aurora's backup and restore. Automated backups are always enabled on Amazon S3. You can take database snapshots at any time with no performance impact. If the database fails, Amazon Aurora automatically attempts to recover your database in a healthy availability zone with no data loss. In the unlikely event that your data is unavailable within Amazon Aurora storage, you can restore from a database snapshot or perform a point-in-time restore operation to a new instance. You can share snapshots with different AWS accounts, upon which the recipient can use the snapshot to restore the database, useful when sharing the same database between various environments such as production, dev, testing, staging, etc. You can choose to make your snapshots public. You can share manual snapshots with up to 20 AWS account IDs. Beyond that, you have a choice to make the snapshot public or request an increase in your quota. You can share snapshots in all regions where Amazon Aurora is available. However, the sharing must be within the same region as the account that shared it. Amazon Aurora supports two kinds of replicas: read replicas, and also by creating a MySQL read replica based on MySQL's binary log-based replication engine. You can set up cross-region Aurora replicas, and you can add replicas to that cross-region replica. You can choose to promote the cross-region replica to be the new primary instance. However, thereafter, the pre-existing cross-region replication will no longer exist. You can prioritize certain replicas as failover targets by assigning a priority tier. Contention chooses the replica the same size as the primary. You can change or modify priority tiers at any time without triggering a failover. You can prevent certain replicas from being promoted to the primary instance by assigning a lower priority tier. You can recover your data by creating a new Aurora DB cluster from the backup data that Aurora retains or from a DB snapshot that you saved. Here is an image showing the priority values given to read replicas. You can see in Availability Zone 3, the replica is sized the same as the primary instance and is assigned a priority tier of 0. That means, being the lowest number, it will be promoted to the primary instance in case of failover. Now you see that the primary instance failed, so the replica with the priority tier of 0 has been promoted. Note that you can have different sizes of replicas, which would depend on your workload. It's good practice to test the various types of failures that can happen with your Amazon Aurora cluster to discover if you need to change any settings for better recovery. First, to cause a failure of a component at the database node, you can use the alter system crash fault injection query, which reads alter system crash open square bracket, open curly brace, instance or dispatcher or node, end curly brace, end square bracket, semicolon. The fault injection query takes one of the following crash types: Instance means a crash of the MySQL compatible database for the Amazon Aurora instance is simulated. Dispatcher means a crash of the dispatcher on the master instance of the Aurora database cluster. The dispatcher writes updates to the cluster volume for an Amazon Aurora database cluster is simulated. Node means a crash of both the MySQL compatible database and the dispatcher for the Amazon Aurora instance is simulated. For this fault injection simulation, the cache is also deleted. The default crash type is instance. To simulate the failure of disks for an Amazon Aurora cluster, use the alter system simulate disk failure fault injection query. During a disk congestion simulation, the Aurora database cluster randomly marks disk segments as congested. Requests to those segments will be delayed between the specified minimum and maximum delay time for the duration of the simulation. The syntax for disk simulation is alter system simulate % of failure % disk congestion between minimum and maximum milliseconds, open square bracket, in disk index or node index, and square bracket, for interval quantity, square bracket, year or quarter or month or week or day or hour or minute or second, end square bracket, semicolon. The fault injection query takes the following parameters. Percentage of failure means the percentage of disk to mark as congested during the failure event. This value can be a double between 0 and 100. If you specify 0, none of the disk is marked as congested. And if it's marked 100, the entire disk is marked as congested. Disk index or node index means a specific disk or node to simulate the failure event for. If you exceed the range of indexes for the disk or node, you will receive an error telling you the maximum index value that you can specify. Minimum and maximum means the amount of congestion delay in milliseconds. Disk segments marked as congested will be delayed for a random amount of time within the range of the minimum and maximum amount of milliseconds for the duration of the simulation. Quantity means the amount of time for which to simulate the disk congestion, followed by one of the time units seen on this slide. To simulate a disk failure for an Aurora database cluster, use the alter system simulate disk failure fault injection query. During a disk failure simulation, the Aurora database cluster randomly marks disk segments as faulting. Requests to those segments will be blocked for the duration of the simulation. The syntax is alter system simulate % of failure % disk failure open square bracket in disk index or node index end square bracket for interval quantity open square bracket year quarter month week day hour minute or second end square bracket semicolon. The fault injection query takes the following parameters. Percentage of failure means the percentage of the disk to mark as faulting during the failure event. The values are between 0 and 100 and have the same meanings as for the simulate disk congestion query. Disk index and node index have the same meaning that the simulate disk congestion query does. Quantity has the same meaning as the simulate disk congestion query does. To test an Aurora replica failure, use alter system simulate read replica failure fault injection query. An Aurora replica failure will block all requests to an Aurora replica or all Aurora replicas in the database cluster for a specified time interval. When the time interval completes, the affected Aurora replicas will be automatically synced up with the master instance. The syntax is alter system simulate percentage of failure % read replica failure open square bracket to all or to replica name end square bracket for interval quantity open square bracket year or quarter or month or week or day or hour or minute or second, end square bracket, semicolon. The fault injection query takes the following parameters. Percentage of failure means the same that it did for the simulate disk congestion query. Failure type means the type of failure to simulate. Specify to all to simulate failure in all replicas in the cluster, or specify to, then the name of the Aurora replica to simulate a failure of a single replica. The default failure is all. Quantity means the amount of time for which to simulate the Aurora replica failure event. The interval is an amount of time followed by a time unit. The simulation will occur for the specified unit of time, for example, 30 minutes. Take note, if you specify too long of a time interval, your master instance writes a large amount of data during the failure event, and therefore your Aurora database cluster might assume that your replica crashed and replace it. As you know by now, you can recover data by creating a new Aurora database cluster from the backup data that Aurora retains or from a DB snapshot that you've saved. To determine the latest or earliest restorable time for a database instance, look for the latest restorable time or earliest restorable time values on the RDS console. The latest restorable time for a DB cluster is the most recent point at which you can restore your database cluster, typically within 5 minutes of the current time. The earliest restorable time specifies how far back within the backup retention period that you can restore your cluster volume. You can determine when the restore of a DB cluster is complete by checking the latest restorable time or earliest restorable time. The latest restorable time and the earliest restorable time values will return null until the restore operation is complete. You cannot request a backup or restore operation if the latest restorable time or earliest restorable time returns null. The steps to restore a database cluster to a specified time using the AWS Management Console is to open the Amazon Aurora cluster in the left navigation pane, click Instances, shown by the purple number 1. Click to select the primary instance for the database cluster that you want to restore, shown by the purple number 2. Click Instance Actions, shown by the purple number 3 in this second screenshot, and then click Restore to Point in Time, shown by the purple number 4 and pointed to by the red arrow. In the Restore Database Cluster window, click to select the Use Custom Restore Time option, shown by the purple number 5. Type the date and time that you want to restore to in the Use Custom Restore Time boxes, shown by the purple number 6 and pointed to by multiple red arrows. Type a name for the new restored database instance in the Database Instance Identifier box, shown by the purple number 7. Click the Launch DB Cluster button to launch the restored database cluster. Quiz time for Section 2.7, Understanding Amazon Aurora's Fault Tolerance and Restoration Architectures. Question: what is not true about Amazon Aurora's fault tolerance and restoration? A. You can simulate failure of any number of Amazon Aurora's read replicas simultaneously. B. The lowest numbered priority tier will be promoted to the primary instance upon failure. C. The MariaDB ODBC JDBC drivers automates the process of DNS propagation to the new primary instance upon failure. D. You can share Amazon Aurora snapshots among different AWS accounts. Answer: A. You can simulate failures of any number of Amazon Aurora read replicas simultaneously. Explanation: you can only simulate failures on all read replicas or one individual read replica at a time. This concludes Section 2.7, Understanding Amazon Aurora's Fault Tolerance and Restoration Architecture. Coming up next is Section 2.8, Amazon Aurora's Performance.